This is Lecture 2, Review of Collecting and Describing Data. By the end of this lecture, you should be able to construct a conceptual and operational definition of a variable, enter data into SPSS and read data in SPSS, classify a dataset based on its unit of analysis, identify a variable's level of measurement, calculate and interpret the mode, median, and mean of a variable, construct and interpret a bar graph and histogram of a variable, and calculate and interpret the standard deviation of a variable. In the previous lecture, I briefly reviewed the basic steps in conducting a statistical analysis in political science research. Before I go into more detail on how to conduct statistical research in political science, first I need to teach you how to measure concepts and variables. If you do not know how to measure concepts and variables, you will not be able to conduct any statistical analyses. Hence, the first part of this lecture is all about collecting and measuring data. Political scientists study concepts such as liberalism and conservatism, inequality and inequality. These concepts are not tangible. You cannot touch them or hold them in your hand. You cannot see them. You cannot hear them. Nevertheless, we know these concepts exist. They exist as mental constructs. Since these concepts are mostly mental constructs, we have to make sure we have a good definition of what they are if we want to measure them and collect data on them. For example, we may have a general idea of what war looks like. Two states may use physical force against each other, they may destroy each other's property, and there may be battle deaths. However, not all conflicts between states are wars. Sometimes two states will have a single battle in a single day and the conflict will end. Is a one-day conflict a war? Not really. So how do political scientists distinguish between wars and short-term conflicts? One way is to use battle deaths as a criterion. The Correlates of War dataset classifies any conflict between states with 1,000 or more battle deaths as a war. In this part of the lecture, I will show you how to define concepts so they are measurable. In order to measure a concept, we need to develop a more concrete idea about what the concept means. The first step in this process is developing a conceptual definition of a concept. A conceptual definition is a concrete and well-specified definition of a variable. It tells us what we have to observe in the real world to measure the variable. A conceptual definition first includes the unit of analysis. The unit of analysis tells us who or what the concept applies to. Is it individuals? Is it parties? Is it countries? Or is it pairs of countries? It also tells us where they exist and when they exist. The conceptual definition also identifies a concept's measurable properties that we can observe in the real world. Here is an example of a conceptual definition for ideology. Individuals who are liberal believe that it is appropriate for the government to redistribute resources from the wealthiest citizens to the poorest citizens. Individuals who are conservative believe that it is inappropriate for the government to distribute resources from the wealthiest citizens to the poorest citizens. Note that individuals is the unit of analysis, as it tells us what the concept applies to. Individuals have ideological beliefs. Note that the following information tells us what the variable's measurable properties are. We know an individual is liberal if they believe that it is appropriate for the government to redistribute resources from the wealthiest citizens to the poorest citizens. We know an individual is conservative if they believe that it is inappropriate for the government to redistribute resources from the wealthiest citizens to the poorest citizens. In the next few slides, I will show you how to develop a conceptual definition. As an example, we are going to develop a conceptual definition of democracy. The first step in creating a conceptual definition of a variable is to identify the variable's unit of analysis. Recall that the unit of analysis tells us who or what the concept applies to, who or what they are, and when they exist. The who of a unit of analysis could include a lot of different types of individuals or entities. It could be individuals such as survey respondents, students, candidates, legislators, or judges. The what of a unit of analysis could include a lot of different types of entities. It could be political parties, countries, or international organizations. The when of a unit of analysis tells us when the who or what existed in time. It could be in days, months, years, or even centuries. Imagine we were collecting data on the level of democracy a country has. Imagine we were examining countries in the year 2017. Here is the unit of analysis for the democracy variable. Since a democracy applies to countries, countries is the unit of analysis, and I indicate what year I am examining these countries in 2017. Although the unit of analysis seems like a basic concept to grasp, many students make mistakes when trying to figure out what a variable's unit of analysis is. Sometimes students think it is the name of the variable. This is incorrect. Sometimes students think it is the concept the variable is trying to measure, like war or democracy level. This is incorrect. Once again, the unit of analysis is the subject of the dataset. It is what is being measured and when it is measured. So imagine you were gathering data on voter turnout in states in 2017. The unit of analysis for this variable is not voter turnout. It is not voter turnout in U.S. states in 2010. The unit of analysis is just states in 2010. What is being measured in this variable? The U.S. states. When is it being measured? 2010. The next step in developing a conceptual definition is identifying the concept's measurable properties. These are properties we can observe in the real world. For example, if we were writing a conceptual definition of democracy, the measurable properties of democracy could include whether a country has elections, whether leaders of a country are held accountable for their actions, and whether the country has a highly developed economy. These are all potential properties of democracy that we can actually observe in the real world. After we identify the concept's measurable properties, we have to modify our list just to make sure that we are only including relevant and measurable criteria in the list. For example, in our previous list, elections and accountability were good measurable properties because all democracies should have elections with elected officials who are held accountable for their actions. However, we should leave out the economic development property. Economic development is not an inherent property of democracy. As long as a country has elections and leaders are held accountable for their actions, it is a democracy. Its economy does not have to be developed. A country could be a poor democracy. After we modify our list of measurable properties, we write down our conceptual definition. You can use the following template to write down a conceptual definition. The concept of X is defined as the extent to which subjects exhibit the characteristics of Z. So using our democracy example, we could write, the concept of democracy is defined as the extent to which an individual country holds regular elections and holds leaders accountable for their actions. Democracy is our concept. An individual country in 2017 is the unit of analysis. And holds elections and holds leaders accountable for their actions is the measurable properties. Next, we will discuss how to develop an operational definition. Recall that an operational definition tells us specifically how the concept is measured. The operational definition includes the unit of analysis, the values the variable takes, what those values mean, what we have to do to observe in the real world to determine the value each observation takes, and the source of the data. Here is an example of an operational definition for an ideology variable. The unit of analysis is individuals in 2016. The values the variable takes are either 0 or 1. A 0 means liberal and 1 means conservative. The specific criteria for coding it is as follows. A person who says they believe that it is appropriate for the government to redistribute resources from the wealthiest citizens to the poorest citizens is coded as liberal. A person who says they believe that it is not appropriate for the government to redistribute resources from the wealthiest citizens to the poorest citizens is coded as conservative. and the source of the data is the American National Election Survey. The first step in writing an operational definition of a variable is identifying the variable's unit of analysis. Recall that the unit of analysis tells us who the variable applies to, who or what, and when they existed. The unit of analysis should be the same unit of analysis from the conceptual definition. Using our democracy variable as an example, our unit of analysis from the conceptual definition was countries in the year 2017. The next step is establishing the specific observable criteria for your variable. For example, if we were measuring democracy and we wanted to measure elections, we would specifically examine whether a country has free and fair elections, where every adult can participate and the rules do not favor one party over the other. In addition, we would want to make sure leaders are held accountable. One observable and measurable way leaders can be held accountable is having to face re-election at fixed intervals. The next step in creating an operational definition is identifying the values your variable will take and what those values mean. For example, with our democracy variable, we can make a rule that when we identify a country as democratic, meaning it has free and fair elections and leaders face re-election at fixed intervals, we can give it a value of 1, and all other countries would receive a value of 0. The last step in creating an operational definition is identifying your data sources. Your data sources tell you whether your subjects meet the specific observable criteria in your variable. We can either use data we collected, which is called primary data, or use the data that other people have collected, which is called secondary data. If we wanted to collect primary data, we could use information from news sources, government documents, surveys, or experiments. There are lots of places we can collect data from. Of course, there are a ton of political science-related data sets out there that other scholars have already created, so often it's just easier to use data other people have created instead of creating our own. So in our previous example, we stated that we would classify a country as democratic if it had free and fair elections, where every adult can participate and the rules do not favor one party over the other. In addition, leaders in the country would have to face re-election at fixed intervals. We could use the CIA World Factbook as a data source in this case to determine if different countries throughout the world meet these criteria. The variable we created would be a primary source as we collected it. And here is the operational definition of democracy in full. After we develop our operational definition, we can then enter in the data into a statistical software program. In this class, we will be using a program called SPSS to analyze our data. In SPSS, in the Data View tab, you can enter in the data for your dataset. The first thing you should know is that the column headings should identify the variable names. Typically, the first couple of variables in your dataset should identify your dataset's unit of analysis. So in this dataset, the subjects of the dataset are countries, and the time is the year, 2017. So we know the unit of analysis for this dataset is countries in 2017. The subsequent headings should be the names of the variables. So the first variable in this data set is GDP per capita. Next, the rows are where you can enter in the data for individual observations. So for observation 5, the country is Luxembourg, the year is 2017, and the value for GDP per capita is 109,100. Now, for the most part in this class, you will not be entering data in for your own assignments. Instead, you will be working with data sets other people have created. Hence, you will have to know how to read data sets when you use them. So, if you need to figure out how to read a data set and figure out its unit of analysis, you should use these basic rules right here. However, it is important to note that it might not be possible to follow all of these rules when creating a dataset, and so the structure of datasets vary. For example, it is possible that while the type of subjects in a dataset should remain constant, the time in which data are collected for the subjects might vary. For example, if we were to collect data on countries for GDP per capita and the unemployment rate, we might not be able to collect the data for both variables for the same exact year. While the subjects of the unit of analysis should be constant in the dataset, the time frame may not be, which means that the unit of analysis for each variable in the dataset might not be exactly the same. This is not an issue if you do not want the time frames to be the same or if the data are from within a reasonable time frame, such as within 5 to 10 years of each other. Since there is variation in the structure of datasets, this makes it a bit difficult to figure out what a dataset's or variable in a dataset's unit of analysis is. As such, you can use these tips to help you figure it out. Sometimes the unit of analysis is implied from the dataset name and not included as a variable in the dataset. Sometimes the subjects, the who, the what of the unit of analysis is included as a variable in a dataset, but not the time frame. The dataset name might have the time frame, or the names of the variables might have the time frame. Sometimes the time frame of the unit of analysis is included as a variable in a dataset, but not the subject, the who or the what. The dataset name should indicate what the subjects are. Here is an example of a dataset where it is not clear exactly what the specific unit of analysis is for the dataset. The subjects of the unit of analysis is not included as a variable name, but the name of the dataset is states, and all the data is from the United States, so it is acceptable to assume that the subject of the unit of analysis is the US states. Also, there is no variable in the dataset with a time frame in it. Instead, the variable names seem to have the years listed in them. So for Obama 2012 variable, which measures Obama's vote share in a state, we can assume this data was from the 2012 election. Hence, the unit of analysis for this particular variable in this data set is states 2012. After we write our conceptual and operational definitions and collect our data, we can classify what kind of data set we have. This classification will be based on our unit of analysis. Recall that the unit of analysis tells you who or what the variable applies to and when that who or what existed. Based on the unit of analysis, you can classify your dataset either as a case study, cross-sectional, time series, or cross-sectional time series dataset. This chart here can help you determine what kind of variable you have. If your variable only applies to one subject and you only have a few observations for that subject, then you have a case study. An example of this would be studying democracy in the US in 2017. There would only be one subject, the US, with a couple of observations in 2017. If your variable only applies to one subject, but you have multiple observations for that subject over time, then you have a time series variable. An example of this would be studying democracy in the United States between 2001 and 2017. There would only be one subject, the United States, with multiple observations between 2001 and 2017. If your variable applies to multiple subjects and you only have one observation per subject, then you have a cross-sectional variable. An example of this would be studying democracies in all countries throughout the world in 2017. There would be multiple subjects, all countries in the world, with one observation in 2017. If your variable applies to multiple subjects and you have multiple observations per subject over time, then you have a cross-sectional time series variable. An example of this would be studying democracy in all countries throughout the world from 2001 to 2017. There would be multiple subjects, all countries in the world, with multiple observations between 2001 and 2017. Going back to the democracy variable example, our unit of analysis was countries throughout the world in 2017. In our variable, we would have observations for multiple subjects, all countries in the world, with one observation in 2017. This would make our variable a cross-sectional variable. In this part of the lecture, I'm going to show you how to classify a variable based on the values the variable can take. You can classify a variable as nominal, ordinal, interval, or ratio level. Remembering the word noir is an easy way to remember these four terms, as the letters in the word noir are the first letters of these four words. Noir means black in French. Nominal level variables divide the subjects or observations in your variable into different categories. The categories are exhaustive, meaning that you included all the possible categories. The categories are also mutually exclusive, meaning that you can only place a subject or observation in your data set into one of the categories. And note, while there is numerical difference in the categories, there's no inherent order in the data. One category is not greater than another. For example, if you were collecting data on voters' party identification, you would have three different categories in your data: Republican, Democrat, and Independent. These categories are mostly exhaustive, as they capture the three main party identifications in the United States. These categories are also mutually exclusive because a voter cannot be classified into categories such as a Republican and a Democrat. And even though these categories have different numerical values, there is no inherent order in the variable. Even though independents are given a 2, they are not greater than Democrats, a 1, or Republicans, a 0. Ordinal level variables also divide the subjects or observation in your variable into different categories. The categories are exhaustive, meaning that you included all the possible categories. The categories are also mutually exclusive, meaning that you can only place a subject or observation in your data set into one of the categories. In addition, there is inherent order within an ordinal level variable. For example, many surveys ask respondents about the extent to which they support a candidate. The surveyors divide the support answers into numerical rank order categories, such as strongly oppose a -2, oppose a -1, neutral a 0, support a 1, and strongly support a 2. As you can see, the least support has the lowest value, -2, and as a respondent support increases, the values go up by 1. However, note that while there's inherent order in this data, the spaces between the categories are not inherently fixed. A survey respondent may feel that there's a huge difference between strongly oppose and oppose, but a small difference between oppose and neutral. Interval level variables are ordered. The spaces between the categories are fixed. For example, the spaces between 1 and 2 equal the same distance between 2 and 3, 1 unit. But with interval level variables, there is no true 0. Ideology could be an interval level variable. You could have a continuous ideology variable that ranges from 0, extremely liberal, to 5, moderate, to 10, extremely conservative. But the 0 in this case is an artificial 0. We could have moved the scale from -5 to 5 instead, and 0 would become moderate, and it would not fundamentally change the nature of the variable. Note that because interval level variables have no true 0, we cannot use ratios or percentages with them. Since there's no true 0, it is just an arbitrary marker. There is no 0 of something, so there can't be a percentage increase or in something. To illustrate this with the ideology variable, since there is no true 0 in the variable, there is no 0 of something in the measurement, so there can't be a percentage increase in something in the variable. Last, ratio level variables are ordered, the spaces between the categories are fixed, and ratio level variables have a true 0. Military spending is a ratio level variable. Military spending ranges from 0 to any positive value. And because there is a true 0, we can use ratios and percentages with this data. For example, $2 of military spending is 100% more than $1 of military spending. Next, I'm going to show you how to use basic statistics to describe data. First, I will discuss measures of central tendency. Central tendency is just another way of saying the average or typical case of a variable. There are 3 measures of central tendency: the mode, median, and mean. The mode is the most common or most repeated value in the variable. In order to find the mode by hand, you arrange the values from the smallest to the largest, then you find the most repeated values in the variable. To demonstrate how to figure out which value of a variable has the largest number of observations, I will use common space scores from the 106th Congress. Common space scores measure House members' ideological positions by using roll call votes. Common space scores range from -1 to 1, with values less than 0 being liberal and values greater than 0 being conservative. In this particular example, I arranged the data from the smallest to the largest value. There were two modes in this data. The mode for Democrats was -0.374, and the mode for Republicans was 0.359. In both cases, there were 6 observations with a value of -0.374 and 0.359. There were no values in the dataset where 7 or more observations share the same value. The second measure of central tendency is the median. The median is the middlemost value of a variable. It cuts the variable in half with the lowest 50% of values on one side and the highest 50% of values on the other side, on the upper side. To find the median by hand, you arrange your variable from the smallest to largest value. Then you find the median observation number. The position of the median when you have an odd number of observations is equal to the number of observations plus 1, and that value divided by 2. In our common space score example, there were 437 observations. 437 plus 1 is 438. 438 divided by 2 is 219. The median observation number is 219. I arranged the data from the smallest to the largest value. Observation 219 has a value of 0.137. So the median is 0.137. If the median House member has a common space score of 0.137, who do you think controlled the House of Representatives, Republicans or Democrats? It was Republicans. Recall that the common space scores greater than 0 indicate a House member is conservative. The median tells us in this case that the average House member is conservative, indicating that Republicans control the House of Representatives. I showed you how to find the median for a variable with an odd number of observations. Now I'm going to show you how to find the median for a variable with an even number of observations. With an even number, the position of the median calculation will produce a number that will have a 0.5 as a decimal at the end. The median is the average of the values for observations below and above the position of the median number. So let's say we have a common space variable with 436 observations. We would run the same calculation as before. The position of the median when you have an even number of observations is equal to the number of observations plus 1 and that value divided by 2. We get a number with 0.5 at the end. So what we do is we take the observation that is below this value and the observation that is above this value and find the average value of those two observations. If we have 436 observations, our calculation would produce 218.5. So we should take the average of observations 218 and 219. Observation 218 had a value of 0.135. Observation 219 had a value of 0.137. The average of 0.135 and 0.137 is the sum of these two numbers divided by 2, or 0.136. The third measure of central tendency is the mean. The mean is the sum of a set of values divided by the total number of observations. Formally, the equation looks like this. X bar means the mean of X. Any variable name with a bar over it indicates it is the mean of that variable. The Greek letter sigma, capitalized, means the sum of. In this case, it means the sum of all of the observations in X, and n equals the number of observations. For our common space score example, the mean of the common space scores are the sum of the common space scores divided by the total number of observations. I calculated this by hand. The sum of the common space scores was 21.788. The total number of observations was 437. 21.788 divided by 437 equals 0.05. The mean of the common space scores was 0.05. So, in sum, there are three different measures of central tendency, the mode, median, and mean. And all of these three measures give us different values, as in the common space score example, leading us to draw different conclusions about the average or typical case of a variable. So when do we use these three different measures? If we are examining a nominal level variable, we should only use the mode. Recall that the values of a nominal level variable have no order. The mode does not assume a variable has order, but the median and mean do assume a variable has order. Hence, with the nominal level variable, we only use the mode to describe the typical case of a variable. With an ordinal level variable, the values of the variable have order, but the spaces between the values are fixed. We can use the mode for an ordinal level variable because the mode simply tells us the most common value in the data. We can also use the median because we can order the data from smaller to largest and find the middlemost value. We can also use the mean, but it is debatable whether it makes sense to use the mean for an ordinal level variable. The mean assumes that the spaces between the values of a variable are fixed, which is not always the case with an ordinal level variable. Nevertheless, social scientists often use the mean to describe an ordinal level variable. Next, recall that interval and ratio level variables are ordered and continuous. Hence, we can use either the mean, median, or mode to describe the typical value of these types of variables. Now, going back to the common space scores example, recall that the common space scores are ordered and continuous. They do not have a true zero, though, so common space scores are interval level. Hence, we can use the mode, median, or mean to describe this variable. However, the mode, median, and mean tell us different things about the typical value of this variable. According to the modes, the typical members of the house are either liberal, a score of negative 0.374, or conservative with a score of 0.359. According to the median, the typical member is moderately conservative with a score of 0.136. And according to the mean, the typical member is moderate with a value of 0.05. So which one of these is correct? It depends. We really cannot make an informed judgment about which one of these to use until we examine how the values of the variable are distributed in a bar graph or histogram. In the next couple of sections, I'm going to show you how to create bar graphs and histograms. Then I'm going to show you how to use them to decide which measure of central tendency to use to describe a variable. A bar graph is a visual representation of how many observations in our variable fit into specific categories in our variable. As such, it is best used for nominal and ordinal level variables. To illustrate how many observations fit into each category, we use bars, hence why it's called a bar graph. When you construct a bar graph, you place the total number of observations or percent of observations on the y-axis and the category names on the x-axis. Then you add bars on top of the categories on the x-axis to represent how many observations fit into each category. This is a bar graph that represents the information from a polity 4 frequency distribution. The polity 4 dataset classifies countries into autocracies, anocracies, or democracies. As you can see, the percent of observations is on the y-axis, and the category names are on the x-axis. Note that I placed the variable name below the x-axis as well. 20% of the observations were autocracies, so the top of this bar for autocracies extends to 20% on the axis, on the y-axis. 50% of the observations were anocracies, so this bar on top of anocracies extends to 50% on the y-axis. And 30% of the observations were democracies, so this bar on top of democracies extends to 30% on the y-axis. To interpret this bar graph, we would say 20% of the cases were autocracies, 50% were anocracies, and 30% were democracies. Now I'm going to briefly describe how histograms are constructed. A histogram is just a special kind of bar graph for interval and ratio level variables. If we made a bar graph out of an interval or ratio level variable, then we'd have to put a category on the x-axis for every single value of the variable, which would be a lot of categories. With so many categories on the x-axis, the graph wouldn't be visually appealing or informative. So instead, we create categories or bins on the x-axis that represent a range of values for the variable. Then we count to see how many observations have values that fit within the range of the values for each category. Hence, the bars represent the total number or percentage of observations in the variable that fit within the range of values for each category. Here's an example of a histogram of the common space scores from the House in the 106th Congress. Recall from the beginning of the lecture that common space scores measure Congress members' ideological leanings from -1 to 1 based on their voting behavior. As you can see on the x-axis, these bars do not represent specific values in the variable. Instead, each bar represents a range of values. This makes the graph more informative and visually appealing. If there was a bar for each common space score value, the graph would be very cluttered, messy, and hard to interpret. So what does this histogram tell us about the typical member of Congress? We could say something like, there was not one typical House member in the 106th Congress. Instead, there were two typical House members in the Congress, a liberal Democrat and a conservative Republican. About 42 House members were liberal Democrats. Liberal Democrat here, 42 here. And about 50 House members were conservative Republicans. Conservative Republican about here, 50 here. Now I'm going to show you how to describe a bar graph or histogram for ordinal, interval, and ratio level variables using the following characteristics: center and spread, number of peaks or modes, and skewness. The center of a bar graph or histogram is where the median is located. You can calculate this by hand or use SPSS to do it, which you will learn how to do in the next lab video. The simplest way to calculate the spread of a bar graph or histogram is to take the value of the largest observation value and subtract the value of the smallest observation value from it. So, for example, in this bar graph, the center or median is 50, the spread is 90, the largest value, minus 10, the smallest value, which is 80. The next characteristic of a bar graph or histogram that you should describe is the number of peaks and where they are. A peak is like a mountain peak. It creates a clear upward pattern in the data with other bars following that pattern and eventually clustering around it. To find a peak, draw a general outline on top of the bar graph or histogram. Here is a histogram of states' vote share for Gore in the 2000 presidential election. I drew a general outline on top of it. From this outline, I can see there is one clear peak around 45. There is an upward trend to this peak that the other bars follow. And these bars here are clustering around the peak. Here is a histogram of the Heritage Foundation's ratings of government spending. I drew a general outline on top of it. From this outline, I can see there is one clear peak around 80. There is an upward trend to this peak that the other bars follow. It is like these bars are building a stairway up to the peak. And these bars here are all clustered around the peak. Here is a histogram of the UN's Gender Inequality Index for countries around the world. I drew a general outline around it. From this outline, I can see that there are two clear peaks, one around point 3 and one around point 7. There are two distinctive upward trends with bars clustered around them. A smaller one around point 3 and a larger one around point 7. With this graph here, the upward trend to the one peak looked like stairs. There is no other distinctive peak in the graph. But with this graph here, the two upward trends looked very different. They're very distinctive, with bars clustered around both. Now, when you describe the peaks in the graph, you should note how many there are and where they are at. If there is only one clear peak, the graph is unimodal. If there are two clear peaks, the graph is bimodal. If there are many clear peaks, the graph is multimodal. And if there's more than one clear peak, note if the peaks are about the same size or if one is bigger than the others. Also note, as this is a bit confusing, that calculating the mode by hand is different than identifying the mode or modes in a graph. Here is an example of a graph that is unimodal with one mode at 50. There is one clear peak. Here is an example of a bar graph that is bimodal, one mode at 0 and the other mode at 100. There are two distinct peaks. Note that the peaks are about the same size. Here is an example of a histogram that is bimodal with one mode at negative 0.4 and one mode at positive 0.4. The 0.4 mode is larger. The next characteristic of a bar graph or histogram that you have to describe is skewness. If a bar graph or histogram has a negative skew, then the left side of the graph extends much further than the right side of the graph. If it has a positive skew, the right side of the graph extends much further than the left side of the graph. If there is no skew, the left and right sides of the graph extend about the same amount from the center of the graph. You could fold it in half and the shapes would be the same on both sides. This is an example of a bar graph with a negative skew, as the left side of the graph extends much further than the right side of the graph. Here is a general outline on top. As you can see, the left side is extending much further than the right side. It's extending into a negative direction, hence a negative skew. This is an example of a bar graph with a positive skew, as the right side of the graph extends much further than the left side of the graph. Here's a general outline on top. As you can see, the right side is extending much further than the left side. It is extending into a positive direction, hence a positive skew. This is an example of a bar graph with no skew. It's the left and the right sides of the graph extend about the same amount from the center. You could fold this distribution in half, and the left and right sides would be about the same. In the next 5 slides, I'm going to give you examples of how to use center, spread, modality, and skewness to describe bar graphs and histograms. In this graph, the center is 50, which I calculated by hand, but you can also use SPSS to do it. The spread is 90, the largest value, minus 10, the smallest value, which equals 80. The graph is unimodal with one mode at 50, and there is no skew as the left and right sides of the graph extend about the same amount from the center of the graph. In this graph, the center is 50, the spread is 100, the largest value, minus 0, the smallest value, which equals 100. The graph is bimodal with one mode at 0 and the other mode at 100. The peaks are even, and there is no skew as the left and right sides of the graph extend about the same amount from the center of the graph. In this graph, the center is 50, the spread is 100, the largest value, minus 0, the smallest value, which equals 100. The graph is bimodal with one mode at 0 and the other mode at 100. The peaks are not even. The 0 peak is the larger mode. And there is no skew as the left and right sides of the graph extend about the same amount from the center of the graph. In this graph, the center is 50, the spread is 70, the largest value, minus negative 10, the smallest value, which equals 80. The graph is unimodal with one mode at 50. In this graph, there's a negative skew as the left side of the graph extends much further than the right side of the graph. In this graph, the center is 20, the spread is 70, the largest value, minus 10, the smallest value, which equals 60. The graph is unimodal with one mode at 10. In this graph, there's a positive skew as the right side of the graph extends much further than the left side of the graph. Now I'm going to teach you an additional way to describe the distribution of a variable, the variance and standard deviation. Consider these two histograms of two different variables. Each variable has the same mean 50, and each variable has the same spread, 100 minus 0, which is 100, and each graph has one peak, they're unimodal around 50, and each one has no skew. Yet the variables look distributed in different ways. If you examine the variable on the left, the distribution is more peaked around the mean of 50, meaning many observations take values closer to 50. But with the variable on the right, the distribution is more flat, with many observations taking values far away from 50. On the left, we would say there's less variance. On the right, we would say there's a lot more variance. We can calculate two numerical values that tell us by how much a variable's observations deviate from its mean on average. Those values are called the variance and standard deviation. I will show you how to calculate them. First, the sample variance, denoted by an S squared, is the sum of each observation minus the sample mean squared, and that value divided by the total number of observations minus 1. Next, the sample standard deviation, denoted by the letter S, is simply the square root of the sample variance. In order to show you how to calculate the sample variance and sample standard deviation, I will use a variable called % living below $2 per day. There will be 10 observations from less developed countries. In order to calculate the sample variance, you start by taking the sample mean of your data. Recall that the mean is just the average of all the cases. So let's say we collected data on the % of people living under $2 a day in 10 countries. The overall mean for this data was 29.4. Then you subtract the sample mean 29.4 from each observation. So for country 1, you calculate 46.1 minus 29.4, which equals 16.7. For country 2, you calculate 60.4 minus 29.4, which equals 31. And you continue this process for each observation. Note that all we are doing is calculating how far each individual observation deviates from the mean of 29.4. Next, you take the values from step 2 and square them. So the calculation for the first observation would be 16.7 squared, which equals 278.9. And the calculation for the second observation would be 31 squared, or 961, and you continue this process for each observation. Note that we square the values to get rid of the negative deviations. It is impossible for an observation to negatively deviate from its mean. Next, you add the values from step 3 together. In this case, the value is 5,840.4. Then you take the value from step 4 and divide it by the number of observations minus 1. In this case, the number of observations was 10, so 10 minus 1 is 9. So the calculation is 5840.4 divided by 9, which equals 648.9. So the variance for % living under $2 a day sample is 648.9. Note that all we are doing here is calculating the average deviation from the mean here. We add all the deviations together and divide by the total number of observations minus 1. That is almost like calculating an average. Last, you take the square root of the variance to find the sample standard deviation. We take the square root because we squared the values in step 3. As a result, the values of the variable become much larger. So we take the square root to bring the number back to a more realistic level. In this case, the square root of 648.9 is 25.5. So our standard deviation for the percent living under $2 a day is 25.5. Now we can interpret the mean and standard deviation. To interpret it, we should start by stating the mean of the variable. Then we would say in our sample, observations deviated about standard deviation units from the mean on average. So applying this to our example, we would say, on average, 29.4% of people in LDCs live below $2 a day. However, in our sample, observations varied about 25.5% from the mean on average. Note that I only use percentage signs since the variable is measured in percentages. Use whichever units the variable is measured in.